In this video, we're going to look at a property of random variables called the expected value. And we'll derive it and practice with it here in the context of discrete random variables. And then when we move on to continuous random variables, we'll see the analog of how we calculate it in those cases. That will be in a future video. So as we've seen so far, there's several ways to describe the distribution of a discrete random variable. We can give the actual distribution function. Another name for that is the probability mass function. Sometimes we can do that in a closed form, like a nice formula that works for all possible cases. If not, we can just write that probability mass function as a table. And then we can also visualize via a histogram. That's defining a given discrete random variable. But we're oftentimes interested in summarizing some properties about that random variable. And two such properties are what's called the expectation, or the average value of the random variable, and the variance, which is really measuring the spread. Both of those properties are numbers. They're not random. And in this video, we'll go through the definition of the expectation. In the future video, we'll go through the definition of the variance. So let's actually start with an example. Let's use the game roulette as an example. So this has a wheel that has 38 different compartments. 18 of them are red, 18 of them are black, the corresponding numbers 1 through 36. And then there's two green ones that are the numbers 0 or 00. As an aside, there are some roulette boards that actually have a third green 0, but we're just going to stick with this form here for this example. So you can place all kinds of bets on various number or color combinations, and each type of bet's going to pay out a different rate. In general, once you set a bet, then they spin the wheel, and a small ball is spun in the opposite direction, eventually comes to rest within one of these compartments. So let's look at the case where you bet $1 on any particular number. Like, let's say we're going to bet on 27, the number 27. If the ball lands on the number 27, then my net winnings is $35, which means the casino gives me back my original dollar that I bet, plus 35. Okay, so let's say I decide to bet $1 on the number 27. And just for the sake of understanding what will happen in the long run, let's suppose I repeat this 100 times, every time I'm still betting on 27. And I write down my net winnings for each trial, and then take the average. So maybe on the first trial I lost and my net winnings was -1. And then maybe I lost again and it was -1. And then maybe I got really lucky on the third time and my net winnings was 35. I'm going to keep doing that. So I get a total of 100 data points, and then I take the average. So again, just a reminder what I mean by net winnings. That's the amount I receive minus the amount I paid to play. So it is possible to have negative net winnings if I lose. This is just a little warm up. We haven't defined how to do this yet, but just guessing, if you had any type of intuition, what number below do you think is the closest to the number you'd expect to get as your average net winnings out of 100 trials? So think about it for a minute. All right, we're going to create the mathematical foundation for how to calculate this, but first let's do it via a simulation to give you some intuition. So looking at the notebook, we're first going to start by creating a wheel. And so notice we have 38 little slots where our ball can land. So I'm going to create a list that's 38 items long, and I'm actually going to give it the number and the color. So I have the red, the black, and the green. I've created those lists here, and so if I want the list of all of them to create my wheel, I can just actually add these. And you can see now I have a list with all of the possible slots, and it has 38 outcomes. So now to simulate one random spin of this, I can use np.random.choice and put, there we go, and put wheel in, And there we go. There's one random spin, another random spin, another random spin. So if I wanted, say, to spin this 10 times, there's 10, the outcome from 10 spins. And now what I'd like to do is come up with a simulation where I can simulate doing 100 spins and then counting every time 27 red shows up. And so a nice built-in function that's going to help us with this, I'm just going to put it down below to see, is this is_in function. If I do my list A, and then I'm just going to pick one that's actually in there so you can see 31B, it's going to return a NumPy array that's Boolean that is true just where that value occurs and false otherwise. So we're going to use that here. We're defining this function number winnings. It's going to take our number, in this case 27 red. It'll take the board, which was the wheel list we created above, and then we get to decide how many spins we'd like to do. And I have, okay, number of winners here is then going to be np dot is_in. I'm going to do trials, and then let's do this for the number of, let's see, I'll do the number that I put in here. That's the Boolean array, and then if I want to count the number of times I have a true, I can just sum that. Then I get my number of losers, and then I'm going to return my average. So here I would do $35 times the number of winning spins. And then I have a negative $1, I lose $1 times the number of losing spins. And then I want to divide this by my average, or by the total number of spins, excuse me, to get my average. And so if I'm going to simulate exactly what I asked us for when I do this 100 times, let's just run it a couple times. Okay, so first that was a win of 44 cents on average. Here was a loss of 64 cents on average, a win of 80. A loss or a win of 8. So you can see for only spinning it 100 times, I have a huge variance in what could happen. Because again, I have 38 possibilities, and so only spinning 100 times, I'm going to have a lot of range in what may or may not happen. If we wanted to think about this in the long run, like what's going to happen if I were to spin this 1,000 times or 10,000 times and start to see, is there some average net winnings that this is converging to? We can actually start to plot that down here. So let me do it via this plot. We're just doing this now. I'm actually going to go a huge number. I'm going to do 10 million. And we're going to see what number this starts to converge to. Okay, and good. What I'm doing is actually just for this plot, I'm actually just showing us units of 100,000. So I just grabbed some because it takes a while to see how this converges. But we can see in the long run, this is going to converge to an average of -5 cents per game played, which is exactly how the casinos make money. They built that in so that on average, you're losing 5 cents for every dollar that you bet, and they're gaining that money. We can see this up here again. I showed you in the long run, but if you want to just start to increase this number, we'll see that this is going to start to converge to be around -5 cents each time. Okay, so that idea of this theoretical average net winnings, as I redo this simulation or redo this trial or this experiment over and over and over, is what we're trying to capture when we talk about an expected value. So let's go back now to our slides and formalize this. So now let's look at the formal mathematical definition. So we define the expected value, or you'll hear it called the expectation or the weighted average. It is the weighted average of all the values that the random variable can take on. So this is the formal definition, but let's try it. And just so you'll see, it'll come up as mean, expected value, weighted average. It is also the center of mass. Sometimes it's called the first moment as well. So let's go back to our distribution that we've been playing around with and calculate the expected value. So again, what I want to do is take the possible values that my random variable can take on. So for example, it can take on a value of 3, And then I'm multiplying that by the probability that x is equal to 3. And then 4 times the probability that x is equal to 4. And on. I'm going to continue that. That's going to end up giving me 5.9. So a couple things to notice. That value 5.9 doesn't have to be one of the possible values that your random variable can actually take on. It is a weighted average. But we could visualize it as if I had connected this here with some kind of rod, and then I placed this histogram, think of this placing this in 2D, this would be, or 3D, this is the balancing point, basically, of this distribution. So that's why it's also known as the center of mass. So, a couple highlights. This is a number, not a random variable. And it is analogous to taking a sample mean in the following sense. If I were to design a sample that had distributions of 3, 4, 6, and 8 exactly according to these probabilities. So let's just do it with a simple example of 10 students. I want 10% of them to be a 3, so that's just one of them. I want 20% of them to be a 4, so that's two of them. Basically, the data is distributed exactly as this random variable is described. And then when I go to calculate the actual sample mean, I'm just going to be adding up all of these terms, dividing by 10. And notice what happens in that context. If I group the terms, so I have 2 4s, I have 4 6s, I have 3 10s, but then I can really think of that as, okay, I have 3 times the probability of 1/10. I have 4 times the probability of 2/10. It's exactly what we're doing here when you're doing your weighted average. So I want you to think of these as analogous, and we will see some further connection to thinking of sample means versus population means. The caveat here is that when I'm saying it's analogous to the sample mean, that's assuming that my sample is exactly distributed like this random variable. And we'll see when we get into sampling that there is going to be some variation in random samples. They won't always have the exact distribution of their parent distribution. And so this analogy only holds in this case where the distribution exactly matches. Okay, so let's return to this problem and actually calculate that -5 cents mathematically, because we saw it via simulation, but let's see how we're going to get it here. So first, I want to think of what's the probability distribution of x. X is my net winnings, and so I really have only two possibilities. If I lose, my net winnings is -1, I lose my dollar. If I win, my net winnings is 35. And then I want to think of the probability. So most of the time I'm going to lose. In fact, out of my 38 options, 37 out of 38 of the time I will lose. And then I will only have a probability of 1 in 38 of winning, assuming that I'm betting on just one particular number. So that's the probability distribution of my net winnings. And given that, I can now calculate my expected value. So my expected value of x is, all right, I have an outcome of -1 with probability, 37 out of 38. And then I have an outcome of 35 with probability, 1 out of 38. And altogether, that's going to give me -2 out of 38, which is -1 out of 19, which is approximately 5 cents. So let's actually do the same idea now with our famous dice roll example. So take a minute, and I want you to put this on pause and come up with what is the expected value for a fair 6-sided die. Okay, in this example, the probabilities are the same for whether I get a 1, 2, 3, 4, 5, or 6. So really I can factor that probability out front, and just to make it faster, and I'm going to get 3.5. Now we're going to close with some expected values of common distributions. In particular, we'll look at our 3 discrete distributions we've introduced so far, and we'll calculate their expected value. So recall a Bernoulli random variable. That was our experiment that has 2 outcomes, a success or a failure. We've defined the PMF here as this piecewise function. So now if I want to take my expected value, I have two possible outcomes for this random variable. It can either be 1 with probability p, or it can be 0 with probability 1 minus p, which gives me that the expected value of this random variable is just p. That should be consistent with the fact here, here's the Bernoulli distribution for p is 0.4, so my expected value is somewhere right here. Let's look at a few properties of expectation before we look at the next common discrete random variables, because we're going to need these properties when we're deriving the expected value for the binomial. So first, we recall the definition. And then I want to just point out that linearity does hold. So if you take the expected value of a constant times a random variable plus expected value of b, you're just going to get back a times the expected value of x plus b. And again, you could see this as an example if you think of x as having a 6-sided die roll, and if y is 2x minus 1, my expected value of y will just be 2 times 3.5 minus 1. Similarly, we can prove that the expectation of a sum is the sum of the expectation. This proof is a little bit harder to do. We actually need to get into joint distributions to show the proof. So right now on the side, I'm just giving you intuition and not the full proof. You can see the appendix for the proof of the first one, but it really just follows from the definition here. And then this proof will be coming. Proof is coming soon, once we've talked about joint distributions. But this at least gives you some intuition. And the last one is if you take the expected value of a function of x. So that one, this is just a definition. If I take the expected value of g of x, really what I want then is my function and then times the probability that x is equal to k. And we'll do that over all k. So we'll do this in a minute just to show you some examples. Let's now take this idea and apply it to the binomial random variable. So remember, binomial is n independent trials of a Bernoulli random variable. And so if I think of y as the number of successes in n trials, here is the probability mass function for the binomial. And yes, we can actually derive the expected value by using the full definition, but because this has this binomial coefficient, it's kind of messy when you try to do it the long way. So a faster way to do it is to realize that we can write this as a sum of Bernoulli random variables, where x sub I is 1 if we have a success and a 0 else. And these x sub i's are all independent, identically distributed, and are Bernoulli. Oops, let's go back, which means that the expected value of y is going to be the expected value of this sum. And we just showed on the previous slide that we have the property that this will be the same as the sum of the expected values. Okay, but now that's the sum. We just showed that the expected value for Bernoulli was just p. That's from our previous page. So this is p, and that's going to give me n times p. So that's pretty intuitive, especially given when we think of the binomial as the sum of Bernoulli. All right, and lastly, we're going to jump to the Poisson random variable. And we are going to do this based on the definition of expected value. So I'm going to start writing that first. This here is k times the probability. And I just wrote it out in a few terms so we can start to see how we might simplify this. One of the ways that you can see is if I factor out a lambda and an e to the negative lambda from each term, then it's possible to rewrite this whole sum as this times the factored out part. And then what's nice is this is a famous sum here that you may or may not realize or recognize. This is the Taylor series for e to the lambda. So I end up getting lambda e to the negative lambda times e to the lambda, and that's just going to simplify to be lambda. So this is very intuitive in the sense that we defined lambda as the constant that is our average number of successes per interval. So it's consistent that the expected value of x then should be lambda. And that's an overview of expected value.